As I said before, uh, the magnetic the exact solution of the magnetic ordering is not established yet for three-dimensional materials, and the two-dimensional magnetic ordering and magnetic phase transition was solved from the Angsaga, but it is very difficult to understand, and also it is out of scope on this class. And anyway, and there is even though one-dimensional Ising spin chain cannot describe the magnetic ordering, we need to study for the Ising spin chain because it has a basic principle of the magnetic interaction and the magnetic phase transition. Here, at this time, I will deal with the one-dimensional Ising spin chain. And this is a one-dimensional Ising spin chain. At first, let's consider for the without magnetic field on the spin chain without magnetic field. Consider a chain of length n with free ends and zero magnetic field. And here in the one-dimensional spin chain is that from the phonon there are n number of atoms are connected in the one-dimensional case, but in here we should consider for the periodic boundary condition. For example, this is the first, second, and so many atoms in here, but in this case, and here n number of atomic chains, and here this 1 and n are identical with each other from the periodic boundary condition, and therefore in this we can understand that this is a first and second and like this, and we can have the chain and n-1, and here's n number of nth atoms identical with the first atom, like it is atomic chain. We call it one-dimensional atomic chain. It describes a periodic boundary condition, and because we do not take into account the magnetic field in this case, the Hamiltonian can be write down only the exchange interaction term minus j summation for I equal to from 1 to n-1, because n-1 atoms in here, and here sigma I plus 1, and it is why we consider for the n-1 is that by considering n-1 interact with the first n, or the first atom or the nth atoms, and it is identical. And here it is, we assume that it is a periodic boundary condition. Periodic boundary condition with a one-dimensional atomic chain. Here we should consider for the partition function. It is a canonical ensemble, and the partition function is for there are n number of atoms, sigma 1 equal from plus minus 1, and sigma 2, and n number of atoms plus minus 1, and exponential, and beta j, because energy minus beta h, and therefore minus becomes plus, and beta j I equal to 1 n-1, and sigma I plus 1. Okay. Here the exponential summation in the exponential can be think about that product. And anyway, here let's consider for the sigma n equal to is the spin. There are two spins, plus minus 1, in exponential beta j sigma n minus 1 sigma n. It is interaction between the n minus 1 and the n atomic side. Then in this case, because there are two spins, one is that parallel, one antiparallel, and therefore it is exponential beta j plus exponential minus beta j. Therefore, it is 2 cosine hyperbolic beta j. Therefore, the partition function Qn, the summation, we only consider for the sigma n in this case. The sigma n consideration is 2 hyperbolic cosine beta j, and the other term, the other remaining term is that the partition function for the n minus 1. And like this, and there are a number of atoms in here, and consequently we can think about that the 2 cosine hyperbolic function. There are n minus 2 number of cosine hyperbolic function, hyperbolic beta j to the n minus 2 and the q2. Yeah, q2 is that interaction between the first and second atom. It is interaction between first and second. It is a q2 partition function. Therefore, here q2 is that summation for sigma 1 equal to plus minus 1 and sigma 2 equal to plus minus 1 exponential beta j sigma 1 sigma 2. Here in this case, and there are four terms: exponential beta j plus exponential minus beta j, and plus exponential beta j plus exponential minus beta j. Because in the case sigma 1 is plus 1 case, and there are sigma 2 is the plus 1 and minus 1, and sigma 1 is that the minus 1 case, and the sigma 2 is also plus 1 and minus 1 case. Therefore, 4 terms should be considered. Therefore, from Q2 is that 4 cosine hyperbolic beta j. Therefore, the partition function is that 2 and 2 cosine hyperbolic beta j to the n minus 1. It is a partition function for the one-dimensional atomic chain. And we know the free energy has this minus kBt ln qn, this relation. Therefore, it is minus kBt and ln here ln 2 plus n minus 1 ln 2 cosine hyperbolic beta j. And in the thermodynamic limit, for thermodynamic limit means that n goes to infinity, so many atoms, and therefore the constant term can be neglected, and therefore in the thermodynamic limit case, we call it as a thermodynamic limit. And the free energy can have the n kBt ln 2 cosine hyperbolic beta j. As I said, if we know that the free energy, we can calculate everything, and it is it is the case for the without magnetic field. Then important thing is that under the magnetic field, under the existence of magnetic field, and there is no special thing in the without magnetic field. And the one-dimensional Ising spin on the magnetic field. In this case, the Hamiltonian is that minus j summation I equal to n sigma I and sigma I plus 1. And here we assume that boundary condition is the n plus I equal to I from the boundary condition. And in here, in this case, yes, it is n atoms, 1, 2, nth atom connected to the first one. That's why in the previous case, the n is identical to n. Therefore, the summation index goes to n in here. And minus h. H is the magnetic field in energy dimension. And the summation for I equal 1 to n sigma I. Because there are in this case, and let's write down minus summation I equal to n, the first term, j sigma I plus 1, and in the second term, let's denote that, and 2/2 sigma I plus 1, because two interaction. We can write down this one because and it is average between the next nearest neighbor. Therefore, the partition function from the definition, the partition function can be calculated for the n number of spins, and the spin has a plus minus 1, and n number of spins for spin up and spin down state, and exponential for the beta summation for I equal to 1 to n, and also j sigma I plus 1 plus h/2 sigma I plus sigma I plus 1. It is reasonable. And anyway, and the exponential in the argument summation is that product can be represented, and let's denote that this kind of summation as a summation of set for spin system, summation of a spin system, and the summation, this exponent summation can be think about that the product from the 1 to n, exponential beta j sigma I plus sigma I plus 1 plus h/2 sigma I plus 1. Yeah, because x plus y equal exponential x exponential y, and this summation becomes a product, and it is natural to understand. Here, let's introduce the 2x2 transform matrix. And anyway, it is very anyway, spin. The spin can be write down as the Pauli spin matrix, and from the Pauli spin matrix, anyway, and therefore this partition function is kind of matrix. Therefore, in order to have the real eigenvalue, we need to diagonalize of the Hamiltonian, diagonalize this partition function. Therefore, and we should introduce the 2x2 transform matrix. Introduce 2x2 transform matrix. The transform matrix is that the 4 components. One is that P11 means that spin up system. P1 minus 1 means up and down system. And P minus 1 spin down and up. And the P minus 1 spin down system. And therefore it is natural description for as a matrix. It is a spin configuration, and there are 4 different spin configuration for spin up and down, up system, up and down and up, and down spin configuration. In this case, then the spin up state here. When we think about that this field argument, then the spin up system sigma I and sigma I plus 1 also plus 1. Therefore, it is as exponential beta j, and also beta j also, and plus 1 sigma I plus 1 is the 2. Divided by 2 is h, j plus h. In the case of sigma I is 1, sigma I plus 1 is minus 1. In this case, exponential minus beta, because sigma I 1 minus 1 product 1 minus 1 is a 0. Therefore, beta j. In the case also minus 1 plus also, it is exponential minus beta j. And in the case minus 1 is that exponential beta j minus h. Here we can know that the P11 is that exponential beta j plus h, and the P minus 1 whether P1 minus 1 is the exponential minus beta j, and P minus 1 is that exponential beta j minus h. From this transform matrix representation, the partition function is like that the summation for the spin index, and it is a product for the transform matrix, and P sigma 1 sigma 2 and P sigma 2 sigma 3 and P sigma n sigma 1. It is a spin interaction transform matrix. The product, it is a product for the transform matrix, and therefore it is this matrix can be diagonalized. Therefore, we can think about that the summation becomes a trace, and P matrix. And anyway, we know that it is P to the n. There are n number of terms, and it is a degenerated case. Therefore, it is n. And here it is n degenerated system, and therefore, in here matrix P can be diagonalized in eigenvalue. We should find an eigenvalue. Because P has a 2x2 matrix, there are 2 eigenvalues, lambda 1 and lambda 2 in real system. Therefore, in order to get the eigenvalues, we should calculate that the secular determinant for the P minus lambda 1 should be equal to 0 to have the eigenvalue problem. And here matrix P to the n has eigenvalues lambda 1 to the n and lambda 2 to the n for nth degenerated eigenvalue, and also trace for P to the n has that summation for this eigenvalue lambda 1 to n plus lambda 2 to n. Therefore, the partition function is that lambda 1 to the n plus lambda 2 to the n. Therefore, the eigenvalue calculation is important in this case. Therefore, let's calculate for the determinant secular equation. And P is that this matrix. Therefore, let's copy this matrix. I'm sorry. The eigenvalue problem is the minus lambda in determinant. We should consider for the determinant. Let's calculate this one. And it's that exponential beta j plus h minus lambda and exponential beta j minus h minus lambda and minus exponential minus 2 beta j. Then it is that exponential 2 beta j minus lambda and exponential beta j plus h plus exponential beta j minus h and plus lambda square and minus exponential minus 2 beta j. Let's rearrange lambda square minus lambda exponential beta j, and it is 2 cosine hyperbolic beta h, because exponential beta j beta h plus exponential minus beta h, and plus here exponential 2 beta j minus exponential minus 2 beta j. Therefore, it is 2 sine hyperbolic 2 beta j should be equal to 0. The eigenvalue lambda 1 and lambda 2 is that the exponential beta j cosine hyperbolic beta j plus minus square root b square exponential 2 beta j cosine hyperbolic square beta j minus AC 2 sine hyperbolic 2 beta j. Okay. And also, let's assume that lambda 1 is positive and lambda 1 is greater than the lambda 2. And in this case, then the Gibbs free energy and the Gibbs free energy and Helmholtz free energy. And anyway, let's assume that it can be write down the same expression kBt ln qn. It is and you know it is kBt in ln lambda 1 to n plus lambda 2 to n. Then it is minus kBt ln let's write down lambda to the n, then 1 plus lambda 2 over lambda 1 to the n, like this. In other words, it is minus kBt n ln lambda 1 plus ln 1 plus lambda 2 over lambda 1 to the n. In thermodynamic limit, and n considered for the very large, and therefore the free energy approaches to the minus n kBt. Here we assume that lambda 1 is greater than the lambda 2, therefore it is less than 1, and for less than 1 value to the infinity, it goes to 0, and ln1 also 0, therefore it is n kBt ln lambda 1. Therefore, it is that minus n kBt ln and lambda 1 here. Let's copy. Oops, I'm sorry. Copy. Let's write down here. It is that, and ln n kBt minus. And here, because lambda 1 is positive, and it is plus. Okay. Okay, then it can be write down again, and minus n here ln the first term beta j, beta is that in reciprocal kBt and cancel with each other, therefore it is n minus nj and minus n kBt ln cosine hyperbolic beta j, and also here we extracted exponential 2 beta j in the outside, and plus square root cosine hyperbolic square beta j minus 2 exponential minus 2 beta j sine hyperbolic 2 beta j. Okay, and it is a thermodynamic limit for the Gibbs free energy. And in the here, the magnetic moment is that negative derivative with the magnetic field. For 1 over n means that single single magnetic atoms. Here it is a field term. Field term contains let's consider for this one. And anyway, and let's write down is that minus 1 over in the magnetic field term. Now let me go back to here. Here we can write down it is lambda 1 and partial lambda 1, partial h, partial g, and partial lambda 1. And here, from this equation, and partial g and partial lambda 1 is that, and you know, from this partial g and partial lambda 1 is that minus lambda 1 to the n kbt. Yeah, therefore it is that kbt over lambda 1 and then cancel with each other, and partial lambda 1 partial h. Okay. No, I'm sorry. It is beta, not beta j, beta h. Beta h. No, it is not. From this, yeah, here I'm complicate. It is complicate. Yeah, I mistake. Yeah, the first term beta h. It is beta h. Okay. It is beta h and beta h. Okay. Yeah, okay. Yeah, therefore we should calculate for partial lambda 1 and partial h from the above equation, this equation star. The first term is that anyway, it is yeah, not this equation. It is g from the, let's copy. Let's copy this one also. Okay. Then lambda 1 is that it is only plus. Therefore, partial lambda 1 partial h is that beta exponential beta j hyperbolic sign beta h plus, it is to the 1/2, and 1/2 your beta exponential 2 beta j cosine hyperbolic square beta h minus 2 hyperbolic sine 2 beta j to the minus 1/2, and also times the here 2 exponential 2 beta j cosine hyperbolic beta h sine hyperbolic beta h. It is a second derivative inside the term. Let's write down this represented by a. Then let's summarize. In the beta exponential beta j hyperbolic beta h. then the first term is 1 plus or this cancel, and square root a to the exponential beta j cosine hyperbolic beta h. Okay. Therefore, the magnetic moment calculated like this. Magnetic moment is that lambda 1 is that exponential beta j cosine hyperbolic beta h plus square root a, and also here beta cancel with each other, and also exponential beta j hyperbolic sine beta h, and also 1 plus square root a exponential beta j cosine hyperbolic beta h. Then from the numerator and the numerator cancel, because square root a plus exponential beta j cosine hyperbolic beta j, and it is cancel with each other because it is square root a plus. Therefore, it is that square root a exponential beta j sine hyperbolic beta h. In a full expression, square root a terms contains for the exponential 2 beta j, and therefore then if we divide by the exponential beta j in both sides, then it is the numerator becomes hyperbolic sine beta h, and also in the denominator cosine hyperbolic square beta h minus 2 exponential minus 2 beta j hyperbolic sine 2 beta j. It is a solution, exact solution for the one-dimensional spin chain, the magnetic moment. And in here it shows that without magnetic field, the magnetic moment is 0 for all temperatures with respect to there is no spontaneous magnetization. And there is no spontaneous magnetization. Spontaneous magnetization is that magnetic ordering, non-zero magnetic moment without magnetic field for decreasing as a limit for the h equal to 0 limit, but it exhibits there is no spontaneous magnetization. Therefore, one-dimensional Ising spin chain never exhibits magnetic ordering. And there is no magnetic phase transition in one-dimensional spin system. That's why the one-dimensional spin system do not exist for magnetic ordering is that in 1D spin chain there are not enough nearest neighbors, and because in two-dimensional spin system and there are 4 number of nearest neighbor in cubic lattices, for example and there are 4 different nearest neighbor, but in one-dimensional system, and just only the two interactions for nearest neighbors, and energy towards the spin alignment is very small. But in higher dimensions, there are enough nearest neighbors, and the ferromagnetic ordering can occur, especially in two-dimensional spin system. Anyway, but as I said, and higher dimensional, three-dimensional real system. Real system is a three-dimensional magnetic system, and the exact solution is not developed. When you find any solution for the three-dimensional phase transition, and you can get the Nobel Prize. Yeah, okay. And this is until now we discussed for the statistical interpretation of a magnetic ordering, which Ising spin system is the exact solution, and this is and magnetic materials. From the next class, I will deal with the superconductivity.